All right, so today we're going to be covering recursion. It won't take more than just today because we do cover it lightly, and then we'll move on to the last part of the course, which is searching and sorting. Remember that there is no class, there is no lab next week on that Tuesday, so you'll have that full week off at least with respect to this class. For that reason, we really highly recommend that you get that hack, what is the recursion hack, which we do on Thursday. Get that done before the break, so that you're not, doing it after the break or over the break. All right. So to motivate this, what I wanted to start out with is, there we go, is a motivating example here, a demonstration. It's just a basic challenge. I want to print out numbers 10 in a countdown, so 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And then when we get down to the end, we'll just say blast off. It's like a spaceship launch or something like that, right? But I don't want to use a loop, okay? So let's come over here and see what we can do. Now, normally, if I did use a loop, it would look something like this. For int I equals n, I is greater than or equal to, or greater than 0, let's say. I plus plus, or minus minus, because we're counting down, right? And then printf, %d, and the line, I. Right? So that'll print, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And then at the end of it, printf. Once n is 0, we'll print out blast off. Right? Okay? And this is pretty straightforward, right? Hopefully it works. There we go. There we go. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, blast off. But now, you're not allowed to use a for loop to do it. Okay? You're not, okay, well, you can use a while loop of some sort, right? No, you're not allowed to use a while loop. A do while loop, nope, you can't use that. And there are no other loop structures in C. If you're in another language, you're not allowed to use a for each loop, or you're not allowed to use an enhanced for loop, or whatever, right? So you can't use a loop anymore, right? So what can you do? What do you have access to? Functions. You have access to variables, right? How can you do it with just those two things? Let's start by writing a function here called countdown, right? It's not going to return anything. Countdown. Right? And suppose that it counts down from n, right? Because I'm going to use this n right here, and then I want to call my function here countdown on n. And I want it to print out 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, blast off. Now, if I'm in this function, then I'm still not allowed to use a loop, okay? I can't, it's not put your loop into a function. You can't use loops, period, all right? So what could we do? Well, let's think about this. If it was already 0, right? If we had already gotten to 0, what would we do? I would print out blast off, right? Blast off. There we go. If it's not 0, like say it's 10, right? I now need to print 10, so let's do that. Printf, %d, and line, n. But now I need to count down from 9, right? How am I going to do that? Well, I've got n right here, n, right? And if I subtract 1 off of it, now I've got 9. Do I have a function that will count down from 9? Yes, right here. So, count down on n minus 1. That's a recursive function, a function that calls itself. Right? It's self-referential. Now let me go ahead and compile this and see if it works. Yay. We did the exact same thing, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, blast off. To understand how this is working, let's go ahead and kick this down to just 5. And let's bring it over here to the Python tutor visualization tool that we've been using. Right? So how is it achieving that kind of loop control structure where it counts down? Right? It increments, it makes progress towards its termination condition to blast off, et cetera, right? The way that it's working is by abusing the call stack here. Right? So you receive 5 in countdown. When a function calls a function, you are creating stack frames upon stack frames upon stack frames. It doesn't matter that that function is calling itself. It's just calling another function. And so when it calls itself again, after printing that out, right, then it receives a new copy of n being 4, right? 3, 2, and 1, right? And finally, it'll be n is 0. That's what's called a base case. When it's 0, I'm not making any more function calls other than just printing out blast off here. What happens when I start returning from these functions? Now I've got a stack frame on top of a stack frame on top of stack frame. How is it going to work? These just kind of pop off the top, right? And that's what recursion is all about. It's a function that calls itself in order to solve a problem, right? So we were able to succeed in writing a basic loop control structure using recursion. Recursion is just something that references itself. So for example, over here, the classic joke in Google is if you try to look up what recursion is, what do you get? Did you mean recursion? You click that. What did you get? You just click it over and over and over again, right? It's a built-in joke, right? It's a self-reference, right? What is it? You're referring to itself in a never-ending loop here. Yeah. What?
What about a skew?
Oh, what do you mean? Like a skew? Doesn't look like that's going to be a rye. Nope. Is there a joke with that or?
Look at your screen.
Oh, okay, well, I'm looking at it at an angle, but I guess, yeah, if I move in front of it, I do see it that it's askew a bit, right? All right. Isn't that mildly infuriating subreddit or something that everything is skewed? Right. Say what?
Do a barrel roll.
Do a barrel roll. Is that how you spell it? Okay, there we go. Thank you for the correction, Google. Okay. Duck. Oh, well, okay, my default is DuckDuckGo, but if I force it to go to Google and do a barrel roll, okay, there we go. I'm sure that there are, oh, hey, Star Fox, cool. All right. All right, so anyway, that's what recursion is all about. You've seen this before in mathematics too, right? Let me go ahead and search for, say, fractals or fractal art, right? A fractal is a mathematical object that is a self-reference. So for example, the Sierpinski triangle. I don't know how to spell that. Ski triangle. Either, there we go. There's a Sierpinski triangle. Let's look at this one right here, right? So the rule to create this thing is that you start out with a triangle, and then you remove an inner triangle. Then you recurse, you do the same thing over again on the 3 remaining triangles. You remove that third. Then you do it again and remove that third, that third, that third. You do this infinitely. It's an infinite regression, okay? And it turns out that these things have what's called fractal dimension. Usually things have it's one-dimensional or two-dimensional or three-dimensional. You can actually have things that are fractional between those dimensions, right? Given the precise mathematical definition of what that means. So you see this all over the place in mathematics, right? In coding, however, mathematics here, fractals are self-similar art. In coding, we simply mean that a function is recursive if it makes one or more calls to itself, right? So let's look at the anatomy of this program before we look on here, right? Because we basically used recursion here to simulate a for loop, right? Just a regular old loop. With a loop, there are 3 parts, right? With loops, there are 3 parts. 3 parts. What are those parts? The initialization, the continuation, or the termination, right? Continue and do one more iteration of this loop as long as this condition holds, and the increment, right? Where you are where you are working towards one of those termination conditions. Where do we see those here? Well, where is the initialization? Right there, where you call the actual function. You set your first value, and then you kick off the recursion by calling it on that first value. Where's the increment? Right here, where you are decrementing it by 1 every time you call this function. Where's the termination condition? Right here, where you no longer make any recursive calls, right? You just print blast off and then implicitly return here without making any more computations, okay? So all 3 of those things, initialization, continuation, and increment, have analogs in recursion. The initialization is the first call to your recursive function. Right? The continuation or termination condition is your base case. Base case in the recursive function. Right? The condition by which you no longer you make no more calls, make no more function calls, right? And then your increment, right? Each recursive call must make progress toward the base case, one or more of those base cases, right? We'll go over that again here more formally, but we need another example, okay? And here's the example that I'm going to work with. If you've ever seen recursion before in any other language or Python or whatever, this is always the first example that they show, right? The Fibonacci sequence, where it's an infinite sequence defined such that the first two values are 1 and 1, and then every value after that is the sum of the two previous values. So for example, let's come over here, and let's go ahead and write out the first few values of the Fibonacci sequence. So f of 1 is equal to f of 2, which is equal to 1. Those are my base cases. Right? That's where it all gets started. So 1, comma 1. Now, what's the next value? F of 3 is equal to f of 2 plus f of 1. Right? The two previous values in the sequence, which is equal to 1 plus 1, which is 2. Right? Again, it's just these two values. You sum them up, and then that's your next value. What is f of 4? It's f of 3 plus f of 2, which I've already computed. F of 3 was 2, and f of 2 was 1, so it's 3. Now you don't have to write the math out anymore, right? You can just look at the sequence here. What's the next value? 2 plus 3 is going to be 5, 8, 13, etc. Right? What's next? 21, 34, 55, 89, dot, dot, dot. It goes off into infinity. Right? And it also grows exponentially. It grows very, very quickly. Okay? So let's go ahead and implement this using, or in C. Right? Let's implement a solution to compute the Fibonacci sequence. Now, this is why it's a terrible. It's always the first example people use with recursion, and I'm not going to be any different. But I am going to have a different take on it. It's both an excellent example and a terrible example. It's a terrible example because it shows you why recursion can be bad, and for that reason, I like it as an example because it shows you should probably avoid recursion at all costs when you can. Right? And we'll see why here in a second. First of all, let's go over here, and I'm going to go ahead and get rid of my countdown now. And let's go ahead and create a function here called Fibonacci. Fibonacci. There we go. That's how you spell it, I'm pretty sure. Int n. Now, what I've done here is I've made the return type a long. That's because it's going to be a very, very quick growing sequence. It's going to grow exponentially, and we're going to immediately almost pass 2.147 billion very, very quickly. But with a long, I can represent values up to 2 to the 63rd minus 1, which is going to be in the quadrillions or quintillions, 9 quintillion. So I'm going to be able to compute larger and larger Fibonacci numbers for this. Okay. Let's go ahead and come down here, and let's go ahead and say that we want to compute the 10th Fibonacci number. Right. I will go ahead and put that into a variable called result. Long result is equal to Fibonacci, and let's print it out. Printf Fibonacci of whatever n is equal to %. And then the placeholder for a long is, I think, LD. So n and result. All right. So this has set us up here. Now we actually need to implement this thing. Let's implement it recursively. We're going to need 3 things. We're going to need a base case by which we no longer make any other recursive calls. That's defined right here. When n is 1, we return 1. When n is 2, we return 1. So let's go ahead and write that. If n is 1 or n is 2, then I'll simply return 1. I'm going to put an L behind it because that distinguishes it between a regular old integer and a long integer, right? A long integer is just simply a 64-bit integer, right? Again, I'm just making it larger so that I can actually compute large values, okay? Otherwise, we need to go into this, right? Otherwise, right here. In fact, in math, we use that term. Otherwise, it's this thing right here. It's Fibonacci of n minus 1 plus Fibonacci of n minus 2. That right there is our increment, right? Because we're decrementing n by 1 or by 2, depending on how we're going to end up calling this function. The continuation or base case has already been taken care of, and the initialization here was started over here. I want to compute the Fibonacci of 10. So else is simply just going to be return Fibonacci of n minus 1 plus Fibonacci of n minus 2. There we go. Let's go ahead and compile this and see if it works. The 10th Fibonacci number was what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 55. All right. So let's see if that works. Yay, it worked. Let's go with 11 just to make sure that it's correct. All right. Yay, it works. Now again, I don't like this example because it's kind of a toy example. Nobody in their real life is ever going to compute or even be interested in computing the Fibonacci sequence, right? Not only that, but there's a lot of mathematical mysticism that surrounds it. It's involved in the golden ratio, the perfect ratio, or whatever, in nature and spirals and stuff like that. It's all a bunch of bunk, right? Because that's nothing more than a difference equation, a recurrence relation, a linear homogeneous recurrence relation of degree 2. You can there are an infinite number of those things, right? In fact, in your lab today, you'll look at another one called the Jacob-Stahl equation, right? With just different coefficients here. So big deal, right? Why are we so interested in it? Well, it gives you an opportunity to directly translate the math over here into code, right? There is a one-to-one mapping between this definition right here and the lines of code over here in my program, right? So if you're mathematically oriented, you'd be saying, oh, wow, this is cool. I don't have to learn coding. I know all my math, right? I can go ahead and just write math from now on, right? Well, if you're not mathematically oriented, then maybe it's not so straightforward. That's kind of a subjective kind of thing, right? 89, we're still good. I'm going to bump this up to the, let's go with the 80th, right? 80th Fibonacci number, there we go. Let's just go ahead and bump this up. So it's large, but it's certainly less than 9 quintillion, okay? Let's go ahead and bump this up to 80, and let's see if our program is correct here. Right. Now, while we're waiting for that, I'll come over here and examine. Okay, so it starts with a 2, 3, and it ends in a 6, 8, and 5. Okay. How long should we wait for this? A couple seconds? Well, we've already waited a couple seconds. Right. Minutes, hours, days, what? Years? Okay. Well, this is not that's not a very powerful computer, right? It's just sitting on an AWS platform somewhere, single-threaded, probably throttled to hell. We're just going to go ahead and suppose, though, we'll be very, very generous here, and suppose that we can do 1 billion function calls per second, right? That's way an overestimate on the power of that computer that we're using on whatever's being hosted here, right? So that's going to be seconds. Let's convert those to years. So it'll take about 9 months. Right. Bump it up further. Go to the 81st. Go to the 85th. Go to the 90th. Go to the 100th. And you're talking about centuries. You're talking about millions of years. Right. We'll just let it run here for a little bit while we understand why it is so damn slow. So let's just consider a smaller input. Suppose that we call Fibonacci of 6. Okay? That makes 2 recursive calls. One to Fibonacci of 5 and one to Fibonacci of 4. Okay? Each one of those makes 2 recursive calls. Fibonacci of 4 and Fibonacci of 3. Fibonacci of 3, and Fibonacci of 2. And at that point, I'm not going to write f anymore. Right? 3 and 2, 2 and 1, 1 and 0, 1 and 0, 2 and 1, 1 and 0, 2 and 1, 1 and 0, 1 and 0. There we go. So lots of function calls. Let's write them, or let's count them all up. So for each n, how many function calls were there? So there's 0, 1, 2, 3, 4, 5, and 6. Well, for 6, there's only one function call. For 5, how many do you see? Just that one right there. So that's only one. For 4, how many do you see? 1, 2. Right? For 3, how many do you see? 1, 2, 3. Is that it? Yeah, it should be. What about for 2? 1, 2, 3, 4, 5. I'm pretty sure that that's correct because I see the pattern already. Do you? 8. I'm not even going to bother adding them up. Right? But should it be 8? 1, 2, 3, 4, 5, 6, 7, 8. How did I know that? That's the Fibonacci sequence up. 1, 1, 2, 3, 5, 8. Right? 1, 1, 2, 3, 5, 8. It breaks down at 0. There's only 1, 2, 3, 4, 5. But that's just because it's a weird base case. Right? So the total number of function calls is going to be even larger than the number that you're trying to compute itself. Why on earth would you call Fibonacci of 2 5 times when you could call it once and store that result and then you reuse that result if you need to? And that's going to be our ultimate solution as we look at this in a second. Still running. I'll let it continue running. Right? We'll see if there's a limit on code spaces here. Right? So recursion. Now that we have a sense of what it is it good? Is it bad? Right? So let's take a look at the folks, and I'm going to put on my devil's advocate hat here because I am not one of these folks that would advocate for recursion at all. But let's go ahead and look at it from their point of view. Right? So many problem-solving techniques or approaches are recursive in nature. Right? For example, divide and conquer style algorithms. Just to understand what I'm talking about here, let's do something very, very simple. Right? If I just gave you a bunch of numbers, 8, 4, 3, 7, 2, 9, 8, 4. Right? How would you go about adding these up? Pull out your calculator and start adding? Nah, it's on a piece of paper here. Right? So if you had to do it in your head, what would you do? Okay, 8 plus 4, that's 12. I'm keeping a running total over here in the back of my mind. So that's 12. 12 plus 3, that's 15. Okay, 15. 15 plus 27, now that's 22. And you lose count or you skip one, you accidentally or something like that. How do you do it on a piece of paper?
Use like the arrow.
Yeah. 12, 10, 11, 12, right? It's much easier to add 2 numbers together than it is to add 8 numbers all at once. So we've divided the problem down, right? Instead of adding 8 numbers, let's add 4 numbers instead. That's still too hard. So let's break it down again. Divide it again into 2 numbers, and I can go ahead and compute those easily. Write it down. Do it again. 22, 23, and 45. Right? This is a divide and conquer kind of approach. It's a tournament-style algorithm, right? NCAA will be coming up, not soon, I guess. I mean, they've started, but the final, the NCAA tournament is not until March. And how do you determine who the winner is? This big giant bracket that looks exactly like this, something like this, right? All right. So divide and conquer style algorithms naturally lead you to recursion, right? Recursion allows you to think inductively, or more mathematical, all right? And if you are oriented in that, if your mind is oriented towards math, and you just want to use function after function after function, and you want to set stuff up like that, then great. The vast majority of people don't think that way, though. I don't think that way, and I was a math major when I was an undergrad, right? I still think sequentially, just like a program does. A program says, we're going to execute these commands top to bottom, left to right. That's how we think. That's how we read. Right? That's how we write. We don't think inductively. We don't naturally think inductively. We don't naturally think mathematically. But some people do, right? Many functional programming languages use recursion as their basic structure. So the one that we started out with here, this demonstration of printing a loop, it was not a toy example. There are programming languages in which you do not have loops at all, right? They're pure functional programming languages. Haskell, Scheme, Lisp, a couple of others, where you don't even have variables. You can't set a variable. You only have parameters. You only have functions. You don't have loops. You basically have to use recursion as the basic unit of computation. Right? Now, at the end of the day, those are all going to be run on a machine that is not inductive, that is not functional. It's going to be compiled for a processor that is inherently sequential, right? Parallel, but sequential. The other argument that people would use is that recursion can be simple or clean or mathematical or beautiful or easily understood, right? Right? Just look at this. That was a direct translation, simple code, right? The problem with all these statements is that these are all subjective, right? One person's simple is another person's complicated. One person's beautiful is another person's ugly, right? So unfortunately, all the advantages that people come up with, they're all washed out by the undeniable fact that there are objective disadvantages to recursion, right? You end up abusing the call stack to do your work, right? And if you're going to be abusing the call stack, a lot of bad stuff could happen, right? For example, let me come back over here and steal my code back, the countdown code, right? And restore this. And now instead of Fibonacci, let's go ahead and go with a countdown. There we go. Countdown of n. I'll go ahead and kill this because it is not executing anytime soon. Right? GCC it, run this. So there, it goes 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, blast off. Okay. What if I did a countdown from 1 million instead? 1 million operations is nothing, right? Eventually, though, this is going to crash. Right? If I had written this in a for loop, it would be perfectly fine. It would run perfectly fine. What's happening after about 250,000 function calls here? You're running out of call stack space, exactly. Function call, function call, function call, function call. The dishes are now 8 megabytes high. What happens now the next time you put a dish on top? Stack overflow, right? You are risking that stack overflow, right? This risks stack overflow. Right? In fact, many organizations, and the one I always like to cite specifically is NASA, right? Prohibit the use of blind recursion in their code because of this very reason. Now, we have an 8 megabyte stack space. If you are in an embedded system, you are measuring your stack space in maybe kilobytes or hundreds of kilobytes or something. You cannot afford a deep recursion at all. You wouldn't even be able to get past maybe, 50,000 rather than 100 or 250,000. Right? You're not able to do that at all because you risk the stack overflow. Right? Let's see what else. Yep. Again, you risk the redundant work, right? Fibonacci of 10 makes the same call over and over and over again, recomputing the same values over and over, right? Why call Fibonacci of what was it, 2, 5 different times when you just have to compute it once? And if you save that off and remember that thing, right, then you don't have to ever recompute that value ever again, right? It's called caching, or the way that we're going to look at it is called memoization, right? And that's not a mispronunciation. I'm not having a stroke. Right? All right. You also risk additional time and overhead to do the recursion. Even if you don't overflow your stack, even if you don't have redundant work, you're still making stack frame after stack frame after stack frame after stack frame. That comes at a cost, right? Whereas if you just written a loop, you have one variable, that one variable changes and that's it, right? You don't have stack frame on top of stack frame on top of stack frame that you eventually have to pop off, right? So no matter what, you are risking additional work and overhead, right? We went over this already, but to be more formal about it, when you design a recursive function, you need those three things because you're basically doing a loop. Every recursive function needs one or more base cases, termination conditions in which you no longer do any recursion. Some base cases may perform some basic error handling. For example, over here we didn't do it, but what would happen if, say, if n were less than 1? It's not well defined. What kind of a flag value could we return here to indicate bad input, there is no such thing as Fibonacci of 0 or Fibonacci of -10? Okay, I like that. Why return -1? Does it appear anywhere here in your sequence? Nope. So that's a strong indicator that something went wrong. Another option would be 0. Right? Okay. All right. So some base cases may perform basic error handling. Otherwise, you make one or more recursive calls to the same function. You need to make sure that you're making progress towards one of those base conditions. And of course, the initial call to your recursive function is your initialization statement. Those three things that go into a loop also go into a recursive function. Okay. So I kind of was bad-mouthing it. You know, recursion, who needs it, right? Any language, in fact, any recursive function can be rewritten as a non-recursive iterative algorithm. That's a non-trivial fact, but it's absolutely true. Some languages didn't even started out not even supporting recursion. I think Fortran or COBOL or one of those, the early versions didn't even allow you to have a function call itself because it was thought to be bad. Nowadays, every single programming language that I know of supports recursion. Why? Because I don't know. Don't ask me, right? A lot of people still use recursion because it's cool or neat or it does lead to simple code. But again, you have to be very, very careful about all this stuff, right? That you're not performing redundant work, that you're not risking call stack overflow, etc. Right? Again, some programming language, programming style guides say don't even do it at all. Don't, like NASA. And also, you can always simulate recursion using an in-memory stack. Right? So we're not going to talk about this yet, but later on, we'll look at a couple of sorting algorithms, quicksort, maybe merge sort, that are recursive in nature, but every implementation that you can find does not do the recursion. Instead, the recursion is simulated with an in-memory stack because they don't want to risk that stack overflow. They also don't want to pay for the overhead of function calling, function calling, function. Right? The one that we're going to look at, though, is you can eliminate redundant work using that word that I was talking about, memoization. Right? Now, it sounds kind of like memorization, and it is kind of like memorization. It was coined in the late 60s. I forget who it was. But it comes from is it Greek or Latin? Memorandum. It's probably Latin, right? Like if you write a memo, right, that's short for memorandum, right? You're telling people about something so that they'll remember it. So it's the same basic idea. But memoization is when you use the computer to remember things, right? So if you need to compute a value that has not already been computed, you go ahead and pay for the recursion, right? Just no getting around it. We've decided to use recursion against all advice otherwise. We're just going to go ahead and do it. But we're going to eliminate all of the extra work that goes into it. we're going to go ahead and pay for that recursion when we have to. Right? Then, once the value is computed, you store it or cache it in a table or array. Right? So that the next time you need the value, you check, is it already computed? Right? If so, use it and do not pay, or repay, I should say, for the recursion. All right? That's what memoization is. You're memorizing the previous values of the Fibonacci sequence so that you can use them over again in this, the example that we're going to use. All right? So let's go ahead and outline the solution as our last thing for today. I'm going to go ahead and have pay for the recursion, but I'm going to have Fibonacci with memoization. Right? There we go. Right. So now when I come into the function, I'm not going to have these base cases here. This is the recursion right here. Instead, what I'm going to do is I'm going to outline this. I'm going to check my cache. Right? If Fibonacci of n has already been computed, right, then reuse and return the value. Right? Else, if Fibonacci of n has not already been computed, then pay for the recursion. 1, pay for the recursion. Right? Compute it recursively. But then 2, all right, store that value into your table / cache, right, so that the next time you need it, you can use it. Right? So that's it, right? That's the big idea, right? And in the late 60s, this was such a revolutionary idea that you could actually store stuff in a computer. Right, that it led to a paper, and he coined the term memoization. Right, 50 years later, and yeah, of course you can store stuff in a computer. That's what it's for, right? But back then, that was a revolutionary idea, apparently. Right. So, help me out. How am I going to store my values? These values are long values, and I want to store multiple of them. So, what kind of a thing should I be passing in as the cache? An array. Long star cache. Now, should I be making this const? I won't be able to make changes to it, so how would I be able to put stuff into the table once I've computed it? So no. If Fibonacci of n has already been computed, let's take care of that first. I'm going to check the cache. If the cache of n has already been computed, then I will simply return it. Return cache of n. Now the idea here is that cache of say 1 is going to store the Fibonacci value of 1, right, which is equal to 1. That the cache of 2 is going to store the Fibonacci of 2, which is 1, etc., etc. Oops. Cache of 3 is going to store Fibonacci of 3, which is going to be a value 2, etc. And caches of n will simply store Fibonacci of n. Right? And that's why I'm checking to see if it's been computed. So help me out here, though. This is not C code. This is just regular old language. How can I translate this into something that C will understand? Yeah.
Set all the not compute values to something.
Something? Okay, give me that something. Something that would never be a valid Fibonacci value. No, it's not a pointer, so I can't set it to null. It's an actual long value here. -1 again. I like that again. Or 0, right? So if it's not equal to -1, then that means that it's already been computed, right? A negative value of -1, -1, indicates that it has not yet been computed. And so that's how we're checking for it. Now this other part, else. All right, well, it's not been computed yet. So we need to pay for the recursion and compute it recursively. How am I going to do that? By calling this function again. Fibonacci memoization on n minus 1 and Fibonacci of n, memoization on n minus 2. Making sure to pass in the cache for both of these calls. All right, there we go. Now I could just add those together and return it like I did down here, but that's not going to do me any good if I want to store that result for later computations. Right? That's why I'm going to go ahead and compute each one of them independently. Long b is equal to, and then long result is going to be a plus b, and then store the result in the cache. Right? Cache sub n is going to be equal to result. Then you can return the result. Right? And there was my outline right there. Right? If you want to, we can move that up here. Right? Again, this is cruft. I would get rid of this before I hand it in. Right? This is just my notes to myself. Right? I think we've got a good working Fibonacci with memoization here. All right? Let's come down here and let's call it now. Let's see, 80. We tried that and it didn't work. Let's go ahead and go with Fibonacci memoization of n, right? And we'll print out the result. And then let's get rid of the count down there. Okay. The problem now is, though, I need to give it a cache. So I need to create that cache, first of all. That cache should be how big? Long star cache is equal to, how do I create dynamic memory? Malloc, good. And it's going to be long star. How big does it need to be? Size of int, is that right? It's not an integer, is it? It's a long, so size of long. How many of them do you want? N? Okay. Well, remember how we're using this, right? Cache of 1, cache of 2, cache of 3, cache of n. What about cache of 0? Right? We'll ignore it. Right? Mathematicians like to think in terms of counting numbers. 1, 2, 3, 4. Right? That's why the indexing starts at 1. We're not mathematicians. We are self-respecting computer scientists. Where do our numbers start? 0. So you can go back and correct for everything and subtract off 1, but fine, I'll just ignore it. Right? In which case, I don't want it of size n. I want it of size n plus 1. Plus 1 because if I've got 10, 0, 1 through 10. Right? So I want 11 there. Right? Do I just go ahead and blindly pass it in? Nope. What were my flag values again? To indicate nothing has yet been computed? -1. So let's go. Does cache store a bunch of -1s right now? Nope. So let's go ahead and do that. For int I equals 0, I is less than or n plus 1. That's the actual size, I plus plus. We'll set cache of I equal to -1. Right? Be careful, though. Do you see any base conditions here anymore? Nope. If you're going to use memoization, base cases probably have to be taken care of outside of the function. So cache sub 1, that's equal to Fibonacci of 1, which is 1. Cache sub 2, that's equal to Fibonacci of 2, which is 1. There we go. GCC. Oops. Oh, there. Not even something we were working on immediately there. All right. So come back over here and let's look at, I think that was Fibonacci of 80, right? 2, 3, and then it ends in 8, 5. Let's see if we get the correct answer now. And it's not going to take us 9 months to get it. Excellent. 2, 3, and 8, 5. It was instantaneous. Why? Because there were only 80 computations. Right? We were able to take this tree here, and we were able to trim it. Right? That once we computed, say, F5 here, or let's say F4, the first time we compute it, we stored it off into our table, so that the next time we see it, this entire tree here ends up being cut out. Trimming the tree, what's the other one? Not trimming the tree. What do you do to trees to cut things off? Prune, thank you, right? You end up pruning the trees, right? And this entire computation is now gone, right? A little bit bigger. There we go. You don't end up calling F4 twice, right? You only call it once now. Well, everything else as well. You end up calling Fibonacci of 3 once. That ends up trimming out this entire tree. You end up calling Fibonacci of 2 only once. That trims out this tree. You end up calling Fibonacci of 1 and 0 only once, trimming out this tree. Your tree now looks more like a what? A stick. There we go. Excellent. Stick. It's just you've cut off all the branches, right? Now, of course, it won't survive anymore, but that's much better, right? Now you have fewer leaves to actually rake, right? So we are able to compute, I think, up to Fibonacci of 80. Let's go down here. That's the maximum value that will be storable in a 2's complement 64-bit number. There it is, 1100, and then it ends in a 31. So Fibonacci of 88. That's still correct, right? 1100, and then it ends in 31. You can compare all the rest of them if you want. But if we had to do that with the regular old recursion without memoization, and we use the same, jacked up computer here that is able to do 1 billion function calls per second, seconds to years, you're looking at more like 35 years there instead. Right? So it's an exponential growth, and it's going to end up being an exponential growth in computational resources in order to do that. Right? Now again, the Fibonacci sequence, who cares about it? Nobody's actually going to do this in practice, but you can see a lot of practical applications of this, one of them being what's called dynamic programming, that you may or may not get to in, like, say, Computer Science 3 or something. Right? Yeah?
What does that look like if you put it in Python?
Oh, you mean this entire thing here?
Maybe not the 88, but like 5. I mean,
Okay, yeah, okay, 5. There we go. Let me just copy the relevant stuff, because you said that there was a line limit.
yeah.
Uh,
So then does it make it makes an array then? It stores it?
It'll make an array and it'll store it. Let's do all this as well. Hey, I'm under the limit. There we go. Visualize this execution. There we go. So next. There's the cache. I wanted to compute Fibonacci of 5, and so I create something that is of size 6, knowing that I'm going to ignore 0 right here. Right? I go through and I initialize everything to -1, right? And then I initialize cache of 1 to 1 and 1. Right? And then I start calling this Fibonacci memoization. The first time that I see it, right, it's not that Fibonacci of 5 is not computed because it's -1 right here, right? Right here. And then so it calls Fibonacci of 4, right? Pointing to the same thing here. Calls Fibonacci of 3, points to the same thing. Nothing has been computed yet. And then 2, right? There we go. And it's pointing to that. Then we go down to 1. Or do we go to 1? Oh, we don't? Oh, that's right. We don't go into 1 because it's already been computed, right? It's already part of that table. 2 and 1 are there already. There we go. So that'll end up returning. And guess what? We have recomputed 3, or we've not computed 3 yet. We're about to do that. There we go. Oops, no. Uh-oh. Maybe it ends up calling everything twice. We come back. It should be in there. Okay, there we go. Now it's in there too. I could zoom out. We can see it all at once there. There we go. And then 2 and what is n? N is 2, so it's already been computed, so we use it and return. Right, there we go. And we're going to end up with 3. Now, when this goes and gets the rest of them, it ends up with 5 at the end. There we go. Getting those 2 values, and 5. So this entire array will end up looking like the actual sequence. Right?
But because it still uses a whole bunch of the stack, but because it just makes a pointers in there, it doesn't use up the whole stack.
Yeah, well, I mean, you're going only n deep, right? So you're only go n minus 1 deep. So you're still risking stack overflow, right? But you're not doing all that redundant work, right? The tree ends up looking like this, and so if you've got, like, I don't know, Fibonacci of 1,000, right? Then that will mean that your stack is going to go 1,000 stack frames deep. That's probably reasonable. You could do that, but you would not be able to do, say, Fibonacci of 1 million. That, even though you're not doing redundant work, and even though that will execute within a couple of seconds, it'll still result in a stack overflow. I can run it really quick, and we're not going to get the correct answer because, of course, they're all longs, and it's going to be way too big. Come on. Why are you not? All right, whatever. Let's go with 1 million. 1, 2, 1, 2, 3. There we go. I'm definitely not putting that in Python tutor. There we go. Segmentation fault because of stack overflow. And so what's the ultimate solution? What would you do? Get rid of recursion, get rid of memoization, and only do what? Two variables in a for loop, exactly. Right? Yeah.
What's the ending condition for Fibonacci?
There is no ending. It goes off to infinity. Oh, do you mean the base cases? The base cases would be...
How does the recursive function stop itself?
Oh, if it's been computed before, right? Those are the base cases.
No, I mean in the original one.
This one right here, right?
So you're going, you start at the high level and work down?
Yeah, it's a top-down solution.
So then I guess the
N, n minus 1, n minus 2, n minus 3, until it gets to 1 or 2.
Does it decrement n by 1 and then decrement n by 2?
It does both, right? It decrements n by 1 for one function call, and n by 2 for the other function call. Remember, because we're passing by value, completely new copies get copied onto the program stack.
What does that 1L mean?
It's just 1, but since we're returning a long, I label it as L. So, for example, let me go ahead and give you an example down here. Int x is equal to this. Let me try to compile this. That is way too big for an integer, right?
Yeah.
Right. So, and it's telling me overflow of conversion from long to int. Right. Well, let me go ahead and change this to long. It will it might still complain with a warning. No, it doesn't. It's smart enough. But in some languages, and in fact in C, it's easy. It's safer if you attach an L to this to force it to become a long. Right. Another example would be sometimes you can do this. Float x is equal to 3.14. By default, that might be a double, and it'll have double precision, and then it'll lose the precision when it goes into the float. Or within the code, you can say that, no, treat it as a floating point number immediately. It's basically the same thing as float, kind of. Right? It's just different syntax. I don't even think it's necessary in this case. Where was it? Oh, I missed it. There we go. Don't worry about it. It's just because we're using longs here. Right. Other questions?
Why don't you have to do any kind of calculations with the Fibonacci's? I understand that you're adding the two of them together, but like...
Well, think about the tree here. Right. So, yeah, it's done all the at the bottom. So let's go with Fibonacci of 4. That calls Fibonacci of 3 and 2. That calls Fibonacci of 2 and 1, 1 and 0, 1 and 0. Right? So what ends up happening here is that you add these values together. This is 1, and this returns 1. So add those together, and the result is, let me go ahead and do it in red here, 3. Right? Likewise, over here, the result ends up being 3. Sorry, what am I doing? 2. 1 plus 2. 1 plus 1 is 2. 1 plus 1 is 2. There we go. Fibonacci of 1 is going to be 1, so 2 and 1, when I add those together, becomes 3. 3 and 2, those are returned values that get added, giving me 5. All of the additions, all of the operations are done with respect to the stack calls, right? The return values. Right? So the values here in these trees end up becoming 1, 1. Those become 2, 1 becomes 3, and then over here it was 2 and 1, 1, and then 5. Right? It looks something like that. Do you want to visualize it again?
I'm
No.
just trying to think about it, doesn't make sense.
And I'm with you in some sense, right? Do you regularly think day to day and inductively? Do you regularly think recursively? No, not really. Now, some things you do, right? When you're doing something simple like this, you divide that problem into two subproblems, and then you conquer the smaller problems, because smaller problems are easier to solve, right? Conceptually, at least. So it does make sense from a divide and conquer approach, but it kind of doesn't make sense from a mathematical approach unless you are tuned into thinking mathematically. If you're tuned to thinking in functional programming languages or something, right? And there are those that would advocate as the first programming language some sort of functional programming language like Haskell or Scheme or something like that. That's not too popular, or never was too popular. It's even less popular today. Yeah.
I'm guessing with that they have figured it out, so you don't have to do all the extra grades.
They do. The way that it's done in those languages is called lazy evaluation, and memoization is done under the hood, essentially, that they cache the results so that they don't recompute. You don't have to write the code to do that. It's automatically built into the language. And then there's also lazy evaluation where, okay, well, you set this all up, but I'm not going to actually compute it until you absolutely need the value. Okay, now you need the value. Okay, now I'm going to actually go and do it. Right? So it's lazy. It's called lazy evaluation. Right? Other questions? Recursion?
So,
Yeah, go ahead.
honestly, you're giving me a data doesn't sound that great. Are there any situation where you'd be like, yep, recursion, instead as opposed to a loop?
Me personally, no. There is document traversal, for example, like an HTML document or something. That's hierarchical in nature, right? You've got a tree of data where you've got this root. That root has children. Those children have children. Those children have children, and so it's much easier to think recursively of, I'm at some node here. I can go ahead and make a recursive call for each one of these children. Go ahead and make a recursive call. Sometimes it makes parallelization a little bit easier if you can think in divide and conquer. So, for example, modern computers don't just have one processor, right? They have 4, 8, 16 processors, right? Or modern GPUs, they don't have just one core, they have thousands of cores, right? If you could split that work, if you could divide that work amongst all the other processors, they run in parallel, right? Then you're really getting some power out of your GPU. For that to work, you need to take the problem and be able to divide it, right? And so thinking recursively is a good idea, but then actually when you go to implement it, you probably don't want to do it recursively. There are languages that will automatically parallelize things, or frameworks that will automatically parallelize things if you do it recursively for you. Your mileage will vary though, as for how good it will be done. Right? But I think it's valuable to think recursively and to be able to look at a problem and come up with a recursive solution. But at the end of the day, you probably want a non-recursive implementation in practice. Write a first version where it's recursive, and now let's go back and rework this and use a smart data structure, or simulate the recursion, or use memoization, or some other tool to get rid of that recursion. Or there's another one called tail recursion, where you still use recursion, but you manipulate it so that the compiler can recognize what it can compile away and optimize, so that it doesn't actually have stack frame, stack frame, stack frame, stack frame. It knows, oh, I can optimize this and reuse the same stack frame over and over again for you, right? And it's all opaque, it's all automatic. Right? But we're not getting that deep into the recursion in this class. So if you want, I think my book covers a little bit more of it. Not the Xi books, but the other books. Right? Other questions? Otherwise, it's just a lab today on recursion, and your Hack 12 on recursion on Thursday. Before we leave, though, I want to make sure that we're all on the same page as far as the math goes. Right? So on Hack 12, just a review of basic combinatorics, probably that you got from high school maybe. hopefully. If not, oops, it's not rendering correct. Let's do this. There we go. Okay, now it's rendering correctly. So you're going to end up now it's still not rendering correctly. Come on. Okay, there we go. So how many people have seen this this notation right here? Not many? Or a couple of you? How many of you have seen this notation right here? CNK. If you pull out your graphing calculators, you can see CNK, or something like this, CNK, or maybe the N and K are on the top or on the bottom or something like that. These are binomial coefficients. It's the number of ways of taking 10 people, say, and choosing 5 of them. That's how you read this. N choose 5, right? Or N choose K in general. If you've got 10 people and you need to choose 5 of them for a group photo or something, or a subgroup like 5 people for a committee or something like that. Right? How many ways are there of doing that? One way is to compute using factorials. N factorial is what? So 5 factorial is 5 times 4 times 3 times 2 times 1, right? That's what a factorial is, divided by n minus k factorial. Or the alternative is to use recursion, right? N minus 1 choose k, n minus 1 choose k minus 1. That's called Pascal's identity. Right? Pascal's identity gives you Pascal's triangle. We won't get into that, but you can check it out and see what it looks like. It's the number of ways, again, of choosing k elements from a size of n without consideration of order. So if I chose 5 of you from the 80 or so that are enrolled, right, how many ways are there of doing that? And you can go to Wolfram Alpha and compute those things, right? Let's just go with 10 choose 5. There are 252 ways of doing that. Right? Now, when I choose A, B, C, D, E, right, I'm not doing it with regard to order. That would be called a permutation. These are combinations. So the same 5 people arranged this way, the same 5 people arranged that way, those are effectively the same with respect to binomial coefficients. Right? So now you probably do remember the permutations and combinations. That's high school stuff, right? All right. Okay, good. Just understand that it's just another equation that you can use and then write a recursive solution for. All right. I'll see you in lab.